reasons why we might want to use functional programming. But you could imagine the situation of what if the computers would write the programs for us, and we wouldn't even have to sit there and drink our coffee and not have to do any work. Might be boring, but might be great. So this seems like a pipe dream, and it probably is. But in recent years, this idea has started to gain some traction in reality, and largely, I think, because of improvements in things like SMT technology, solving technology, and things of that sort. And back about 10 years ago, 2005 at PLDI, there was a very important paper, I believe it won the Best Paper Award, on program sketching by Ross and his student Armando Soler-Uzama. And that was, to me at least, that seems like the real kickoff of this whole area of program synthesis, which has become a quite a hot area in the last 10 years. Ross has gone on to work on other things, and among other things, he's been, I guess most recently, been doing DSL-based program synthesis using solvers and to guide program synthesis in narrow domains. He's one of the lead PIs in the Escape expedition, which is funded by NSF, and the expeditions are a really big deal at the NSF, I can tell you. So he's going to talk about that stuff today, I hope. But just to give you a little bit of background, he got his PhD from University of Pittsburgh in '99 on path-sensitive program optimization, and his dissertation, in fact, won the SIG-Plan. Oh, am I not mic'd well enough for you? Oh, okay. Won the SIG-Plan dissertation award. He went on to be a first an assistant professor at the University of Wisconsin, and he moved to Berkeley, and very recently he's moved up here to the North Country, University of Washington. So please give a round of applause to Ross.
Thank you, John. Well, John, thank you for the introduction. This may be too much. Congratulations on the diverse program that I found in ICFP. This is my first ICFP conference, believe it or not. Despite the breadth of the program, I still feel like fish out of the water here, and so may this talk. But I'll try to make it as much as possible about opportunities and problems rather than particular solutions, and we'll see how it goes. What I want to talk about is potentially another revolution in software. One way how you can tell whether industrial revolution happened is to test whether machines are doing the job better, faster, more accurately than humans. And this has arguably happened recently with bug finding and verification, where machines easily beat humans. And this is, of course, thanks to smart algorithms, but I'd say mostly CPU cycles, which these algorithms harness. These algorithms are smart because anything exhaustive just rarely works. But it is largely search, perhaps under the name of constraint solving. So the question I want to ask today, whether we are ready to ask and repeat the same feed in the front end of the software development process, in coding, in design, rather than in the back end, in validation of software that was actually written by a human. So what I have in mind is not the end of programming. I have in mind collaboration, not full automation. So something where the human collaborates with a tool rather than a tool completely takes over, right? Which is what you see on the right. Okay. First, of course, we want to ask whether somebody needs computer-aided programming. And the best way is to go back and see what were the reasons for coining the software crisis. It's fair to say that the group of well-dressed gentlemen on the right who attend the first NASA Software Engineering Conference are responsible for most of you being here, because they raised the problems that led to the definition of various programming models, programming abstractions, software engineering, verification, and so on. Dijkstra is somewhere there at the conference. And so nobody would disagree that software is all right today. Software drives everything. We can write sophisticated software. We seem to be doing all right. So the problem is solved, and with that, we can close this talk and the conference, and you can go home or enjoy Vancouver. Or if you want to hang out while the rain stops, well, let's talk about what were the reasons for software crisis in about 50 years ago. So the first big one was what Dijkstra called gigantic computers. They were not really that powerful. I think they were called gigantic because they were not uniform and hidden under an abstraction. They were really hard to program. In fact, if you read the discussion from the conference, there is a lot of hardware-software co-design going on. So we solved that problem since then by abstracting hardware under a simple ISA, virtualizing many things, including building compilers from reasonably high-level languages like, well, C, better than what they had before. The second problem was the widening gap between ambition and achievement, and we simply solved that by sobering up from experience. So simply, we today don't try to write software that is too ambitious, and therefore, many software projects actually finish on time. Okay, so let's look at two flavors of what hardware looks today, and then we look also at ambitions again. So the first one is concurrency, right? No matter how we abstracted hardware, there is still concurrency lurking on, and because of parallelism, there seems to be more and more going on. And so shared memory comes with interleavings between threads, with stores into shared memory, and that comes with memory models. And those are well known to be incomprehensible to humans. Some of you may know that even the litmus tests, which are short tests that define by example what a memory model should be doing, are difficult for experts to execute, and they get the estimated value, the output values wrong. And it is even better known that memory models actually break optimization that we consider very simple and independent from concurrency setting. The same thing is mirrored in the distributed setting on the sort of internet scale, where you don't have shared memory, under the name of eventual consistency, other consistency models, and there the issue seems to be just similar. So the point here is that we somehow didn't yet find abstractions that would hide these concurrency issues from us. Maybe memory models are just too hard for the human. Maybe we just don't know how to build a compiler that would bridge the gap from something clean and atomic down to the memory model that hardware can feasibly offer. Another source of complexity is the desire to build smaller hardware, smaller form factors, wearable devices. There it boils down to energy efficiency, which Moore's law, as you know, is no longer delivering. So it's mostly up to software now to deliver that efficiency. And so these gigantic computers in the Dijkstra sense, those that are exposing implementation above the abstractions, are essentially back. And again, hardware-software co-design is becoming more important because that's how we can achieve the efficiency that we need. So there are a few application domains that you probably heard of that may require what you could call precision software, software written really carefully by expert programmers. And among them is computing on harvested energy. Here you see a small circuit that harvests energy from radio waves and actually runs a camera on it. Okay. So browser on the smartwatch and other things that would become wearable is another example. So revisiting ambition, we became sober, and that's why mostly projects succeed, or at least we know what we can reasonably fast build. But a DARPA project, BRASS, observes that like a house, software lives 100 years. And so we don't simply throw it out and rebuild a new one, we remodel it, right? So Unix and database are examples of software that were never really thrown out and re-implemented, but slowly remodeled. So one example of this is also the web browser, which is a feat of engineering, and you would not typically re-implement it, but you slowly want to transform it to be parallel, to run on a small footprint, to run on the browser on wearable devices, right? So currently we do all of this by hand, but wouldn't it be nice if you could take a legacy implementation, automatically distill a specification from it, because that implementation often is the only spec you have, and from this spec synthesize a new implementation. That's something we cannot do today. It is a pipe dream. It's something that we take for granted that needs to be manual, but it would be nice to automate it. And that's some of the ambitions that I think should revisit, and that's what the DARPA BRASS program is doing. So what is software synthesis? I think essentially this is all based on the observations that machines can beat humans in bug finding and verification. So could we use cycles to obtain perhaps even superhuman programming, not just faster programming, by harnessing CPU cycles? And it all boils down to abstractions and algorithms for doing this search, or call it constraint solving better. And so if you like abstractions or if you like designing algorithms, hopefully this talk will have something for you. So I want to start with a classical paper and show you how that classical paper evolves into tools that we actually build today that are pretty impressive in their power. Most of you know about Massalin's 87 paper on superoptimization. The problem is easy to state. You are given a specification as a loop-free code. So up here you have the sine function. Okay? It's implemented as cleanly as you can think of. And what it does, it performs an exhaustive search of the space of assembly instructions for the shortest instruction sequence that implements that function. Okay? So here is a 4-line instruction. What is really impressive here is, besides just the guts of attacking the problem this way, is that without too many algorithmic advances, that superoptimizer was able to create instruction sequences between 4 and 13 instructions. So how to use it to build real software besides improving, optimizing compilers, or essentially having a toy demos like what this was essentially? So Alvin Chong from MIT, but now at UW, realized that you can do superoptimization in the inverse direction. So you start from the implementation, which is here. This is a piece of Java code that uses ORM to act as a database and lifts it into a program in a small relational DSL. Why would you want to do it? Because from this DSL, you can easily code-generate a SQL query, which you can then pass into a SQL optimizer and get much better performance. Okay? So we call this translation Alvinization affectionately. It's technically the same as superoptimization because it doesn't really matter whether you go down or up in the abstraction. You're just translating programs between two languages. But this one is really about lifting legacy code. You could say reverse engineering. Right? So what do you gain by doing that? Well, you get about 1, 2, 3 orders of magnitude of performance gains by getting that global view at the problem that the ORM library doesn't have. And the reason here is that if you write a Java application using ORM, it doesn't have the information about the application. It doesn't see the entire loop nest of accesses to the database, which you get by synthesizing this SQL query through a smaller relational DSL. So this is sort of Alvinization as a twist on superoptimization. Now I want to spend a little bit of time on algorithmics and programming abstractions, actually. How does the thing work? Okay? So this is a good point to compare the synthesis that we do by constraint solving or search with this classical 1970s synthesis, which was done by deduction. That started with the program as the specification, and then through various axioms or rewrite rules, you would lower that specification all the way down to implementation. So search does no such deduction. It just performs search in a candidate space of programs, and you can really think of evaluating each of them and checking whether it has the desired behavior. Okay? So it completely sidesteps the semantics preserving rewrite rules and axioms, which are difficult to find in some domains, like sparse matrices. Well, how do you get correctness? You don't get it by construction because you are not obtaining the implementation by rewrites from the spec. You get it by search. So you do it independently. You prove correctness on all inputs by relying on verification. And this QBS system, the Alvinization system I just told you, also synthesizes not just the relational program, but also invariants that you need to perform Horst-style verification. So that's how you can get the verification after the fact. The point here is that these invariants are easier to find, easier to synthesize than the rewrite rules that you would need for deduction, and that's why such synthesizers are typically easier to build. Okay, but you may ask, well, this sounds too good to be true to find programs by search in a huge syntactic space, and indeed it is. So what we see here, the sizes of search spaces that various synthesizers find. So what is this? Here is search space of 10 to the 68. So this synthesizer by stochastic search can explore those search spaces. So depending on how many instructions you are choosing from at each slot, that determines the length of the program that you can synthesize. Okay, so since Massalin, we have made a nice, almost monotonic improvement. These two, well, let's see. Let me tell you about this one. This one is a winner of a ICFP competition from 2 years ago from Boston. Okay? This one doesn't scale as much, but it was written in 2 days, plus 2 nights, of course. And this one here is a winner of another competition. It was written over a long period of time, but it runs in 5 seconds. Okay? This one here optimizes only 3 instruction sequences, but it optimizes all of them. So it would probably scale to bigger spaces, but didn't. Well, so 10 to the 79 is pretty impressive until I show you what are the sizes that you actually do need to search to find a reasonably sized program. So this is the size of the search for MD5, okay? And to get a sense of the scale, this bar ends in my room on the 28th floor of this hotel. So picture the skyline of Vancouver. There is this red bar right there with all the buildings. So clearly, superoptimization alone is not enough. You really need to think of it as a precious resource that you need to carefully allocate, right? Really as a tactical tool. You need to do it carefully. And so this, of course, means, as a corollary, that you need to have a programming model, abstractions, to let programmers actually decide when to resort to this tool, because by itself is not all-powerful. Okay, so let me show you 3 tricks that we use to make superoptimization better and use it on bigger programs. So the first one is a methodology trick. So of course we don't search the space of all programs, or assembly programs even, the way Massalin did, but we restrict the space. How? Well, you can design a DSL. So what Alvin did in QBS, he designed a tiny relational algebra, and he saw how tiny that program was. DSL programs are designed for a domain. They are smaller, and therefore their search spaces are smaller, and that's why many things just work. If you need crazy programs that are intricate, and there doesn't seem to be a DSL for it, what do? You can write a skeleton of the program. That's what we call the sketch. Leave a hole for an expression and just synthesize that. So if we are doing dynamic programming, the skeleton for dynamic programming is obvious. What is crucial is this recurrence function that discovers what are the auxiliary problems you need to solve. So you synthesize just that, sub-expressions in it. Similarly, we are doing SIMD programming, where bit vector shuffling and such is important. Part of the program may look like this. You would leave holes for these so-called magic constants, and you ask the synthesizer to just produce those. So these are all different ways of restricting the space. What's essential here, that they are essentially the same. You are writing a grammar that describes the space of programs, and the grammar is true here, 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 and here, whereas in this grammar, perhaps you are choosing just the constants, but it is all a grammar. Okay? So that's the first trick of making synthesis work. And you can think of it as this here, a DSL is a semantic restriction on the space, whereas these two are more syntactic ones, because you are giving the skeleton of the program and just asking to fill in the rest. The second trick is algorithmic. What we do in the search for the program, we of course don't evaluate those programs when we search for them on all inputs, just on few carefully selected inputs. Why? Because of course, often one input is enough to rule out, to prune out many incorrect programs. So what we do, we grow that set of inputs gradually by counterexample. So inductive synthesizer is another name for that search algorithm, which given the space of programs and a few inputs that sample, we'll find a program that is correct on those inputs. Then it gives us this candidate that is, viable so far. And then you give it to your verifier, which either says, OK, and we are done, or it says, well, here is an input on which this program is incorrect with respect to your specification. We have another counterexample added to the set of samples and repeat. Okay? And this process has the advantage that the sample of inputs is created carefully, because every new input covers a new corner case, not captured by the previous sample. So it is a greedy approximation of what you could say is a perfect test suite. As you may know, perfect test suite is a test of set of inputs which, if your program is correct on those, it's correct on all the other inputs, right? So that's what we are finding here. Now, the third trick is how to take this problem and delegate it to an efficient search algorithm, and that happens in many algorithms today by set solving. So the inductive synthesis problem is this. We have an input-output pair, concrete, not symbolic, x and y, and we are looking for value h, which is sort of a completion of that sketch. You can think of it as a derivation in the grammar or just these magic constants, such that when you plug it in into your sketch, that program, this candidate on x, will output y. Okay? So if you translate it into a Boolean circuit, and the programs, if they have cycles, we unroll them in a bounded fashion into a cyclic program, so a circuit can be created. This is given, this is given, this is free. We're asking set solver to solve for h, right? And that value of h determines that program. If you do that, set solvers will do two important things for free. The first one, they do inverse execution, because all these relations here on the circuit are non-directional. So the set solver can effectively execute the program back from y to h, from x to h, and compute the values of magic constants by simple reverse execution. This is something that Massalin in superoptimization couldn't do. He had to guess those constants and check them. And of course, guessing in a space of constants is much harder than searching a space of just program without constants in them. So you get these magic literals. The second thing that set solvers do, not so well, but mostly pretty well, is pruning. If they find one candidate that is bad, they generalize from it and say, oh, all the other candidates are bad as well. So they may say, well, if this value of this h bit is 0, it doesn't matter what the other one is. That other candidate will be bad as well. Okay? So this is done through conflict clause generation. But there are many things that set solvers don't do well, and this brings me to the first challenge I'd like to pose today. Building a better inductive synthesis algorithm. In fact, I think that what we'll see in 10 years, the solvers for synthesis are not going to look like set solvers at all, but they will be specifically designed for synthesis. So what do solvers do poorly? What do they do well? Well, only if you are lucky. There is no hill climbing towards a better program. Okay? In other words, we cannot take two bad programs, two bad candidates, and compare them and say which of them is less bad. We'd like to see they're both bad, meaning incorrect, but this one is closer to the correct program, so drop this one and start working with that one. So a theory of goodness functions that actually tell you how good the bad programs are in terms of closeness to a correct program would be really, really useful to guide the search in sort of hill climbing fashion. Second, it's not surprising to realize that a space of programs defines a smaller space of functions because there are many syntactically distinct programs that compute the same thing. So if you could do pruning in the space of behaviors, right, defined somehow, perhaps input-output tables or as functions, you would be working in a much smaller space. So you would love to have an algorithm that prunes out behaviors, not syntactic programs. And in fact, some of the more promising algorithms recently are starting to use this, but there are many low-hanging fruits still on the floor to be picked up. What we also need is, of course, native executions. Bit solvers evaluate programs at the level of single bits, not very efficient. So that's here. And we also need jumps in the candidate space. How do the set solvers do the random walk through the space? They flip these bits, the h bits that define the program, going from a program to a program that is completely irrelevant, because that single flip may take you to a program that has nothing to do with the original and may flip an if statement to another branch, for example. So what we would like is a set of mutations. We'd love to walk through the concrete space like the stochastic superoptimizers do with mutations, right? And Herbie, a program for optimizing floating point programs, does something like that with mutations which are taken from the real arithmetic, right? So they take rewrites, so they rewrite this into that. This rewrite is semantically valid in the reals, but it is not valid in floating points, of course, but it is close enough, and therefore a good way of randomly walking that space of candidates. So something like that would be useful tremendously, but if you ask me how to define such rewrites in general, I have no idea. So a theory of rewrites and how to design them would be extremely useful. Okay, now, so much for what synthesis is, what algorithms we have today, and let's start looking into the future. Of course, we want to ultimately synthesize large programs. My particular goal is to make synthesis work for systems, complex software such as web browsers and low-power compilation, and I'll tell you about two projects that do that. Then I'll tell you a little bit about our work on synthesis for systems biology. That's another interest of mine, of how to synthesize models of cells from experimental data. So low-power compilation. So this is an animation that Mangpo, a student of mine, did, and she said, well, here is a programmer working on a CPU today. Problem is that the big CPU power hungry, so the battery is not happy. If you shrink it, the battery becomes happy, but the programmer becomes unhappy because you had to drop the cache in the process, you reduce the size of the memory, you narrow down the interconnect, the bit width of the word. Okay, you drop the interconnect, you had to partition it to make it parallel, and ultimately you go from register-based ISA to stack-based ISA, and then the head explodes. Okay? So of course there is a solution to this that is very traditional, and that is create a good programming model, say data flow or some such, to make the programmer happy. Okay? But of course this just kicks the can down the road to this compiler writer who needs to deal with all of this. And the situation is worse because there is actually many such processors. So the end of Moore's law brought a revolution in how to design new processors. Many questions are open again. It's fantastic if you are in hardware. Okay? So we need a new way of building a compiler. Okay? So that's the story. So here is a specific low-power processor that we are working with. It's by Green Arrays. It's actually done by people who designed the Forth language. Does anybody remember Forth? Okay, so Chuck Moore is one of the designers of the processor. They used to hide near Lake Tahoe. Now they are in Wyoming. And, well, the point is that the processor is extremely power efficient. Here we are running it in my lab on lemon bleach battery. It's not running on many cores, but people have shown how to run it on energy harvesting as well. Anyway, so that's the good thing. The bad thing is that it has 144 tiny cores. So if you think tiny, really think 300 bytes. Not kilobytes, not megabytes, bytes. The words are 18 bits. If that looks funny, think 16 bits plus 2 carry bits that you can do something with in software. Okay? So you need to take your computation and do bit slicing, splicing the computation upper and lower half on 2 cores and somehow carry the value across cores. There is no hardware interconnect. You can write into a latch of your neighbor and wait until the neighbor picks it up, and then you can continue. And if you want to send something across the chip, then of course the software needs to implement this virtual route. There is no hardware bus or anything. And did I tell you there is a stack-based ISA rather than register-based ISA because it's Forth after all? And so no classical optimizations apply. So all the code has been written by hand, and we said, well, let's see if we can write a compiler for it. So the compiler is a sequence of synthesis phases. We cannot synthesize the whole thing. MD5 is the sort of a big benchmark they have written, ran on 5 cores. That's the thing that ends in my room. That's that red bar. And so it's a refinement synthesis in the sense that we do something first and then lower it again and lower it again. What are the refinement steps? We do logical code partitioning first. It's actually posed as a type inference problem. Every piece of memory, every value, every operation has a location, logical location at this point. Certain things are pinned. The algorithm designer may have a floor plan in mind, say this will live here, this will live there, the plus will happen here. And the rest is done with inference to minimize communication cost and satisfy the capacity of every core, the 300 bytes. In the second thing, you take that and you physically place it and do the routing of communication. Then you generate the actual communication code, and then you super optimize to compensate for the fact that you don't have a decent backend optimizer, right? So super optimization becomes your backend single core optimization. Okay? So it's all great, you know. All these phases except for the third one are synthesis phases, which means you formulate as the target of the phase a space of programs, and you need to find a program in that space that is semantically equivalent to the one above. So it's easy to formulate optimally because you say, in this space, find a program that minimizes certain value. And the result is 40% faster than a compiler based on rewrites that heuristically chooses which rewrites, which is nice. And it is, in fact, within 20% of expert-written code, which surprised us because we were hoping for just 2x. Okay. Now, the bad news is that the third step, which was written in a classical rewrite style, the generation of communication code, was done in a classical way. We had to re-implement it 3 times. It was full of bugs. And so the challenge is for how to formulate compiler phases in a synthesis fashion. All of them, the whole slew that we do, so that you don't need to bother with sort of debugging of such compilers in a painful way. Okay. Now, briefly about web browsers. Why do you want to do web browsers and make them faster? You notice that on the laptop or desktop, all new applications are written in the browser, right? There is rarely a desktop application written. Yet if you look at your phone, it's a very different story. Most of the applications are written in this native low-level framework. And the reason is, of course, performance. Right? Browsers are actually like LaTeX with scripting and reactivity in them, and they are quite slow. And so Firefox OS is one of the attempts to build an entire operating system on the browser, right? The idea would be that you write applications on it. Wouldn't it be nice that it would be portable across all phones? And they ran into problems, for good reasons. And one of them is that on mobile, there is just simply not enough performance to run it. And Facebook got burned by building a mobile application on the browser, and they went back to a native one to get better performance. And especially low-end hardware doesn't work really well. And you could say, well, who cares about low-end hardware? But the low-end hardware is actually a good indication of the platforms on which we would really like to run our browsers and rich applications, such as Google Glass, smartwatches, or things that are even smaller than that. So, of course, parallelism is one way of how to make things faster, but it's also a way of how to make it more energy efficient. So here is the result of Servo compared with Firefox. Gecko is the layout engine for it. So this is done by Mozilla Research, a new browser. You probably know it by Rust, which is the language that came out of the project. Here running on 1 thread, here on 4 threads. So you see a significant speed up due to parallelism. What is important is that we were helping Mozilla with the parallelism from the beginning with the energy efficiency in mind. And later, when they really implemented it, we saw that indeed there is a benefit that's significant. So you can look at three cores that are slow and simple. The 3 simple cores will run the browser as fast as a single fast core and save you 40% of energy. So you can really think of parallelism as something that maintains performance and saves energy and allows you to run on smaller devices. Okay, so how is synthesis of parallel layout engine done? So a little bit about layout first. So here is a document tree. It has attributes such as font size, width, height, x, and y, okay? And you solve it if you phrase it as an attribute grammar through several passes. So for this subset of CSS, you have 5 passes. Each of them is parallel, so bottom up or top down, okay? You first compute the font size and some temporary width, then you go up, you compute max and min, and there are 3 more phases after that. So the whole idea, okay, is here. If you know about attribute grammars, you know that attribute grammars come with these local statements, okay, which say this attribute depends on this attribute and some children attributes. And these dependencies define how you need to walk through the tree and compute those statements, okay? So some traversals are simple and easy to state, such as this bottom-up that computes attribute W. Some of them are more tricky, and this is what happens in CSS because you have these islands, these islands of inorderedness here that require you to do small chunks in order so that the whole thing as a one piece actually runs in parallel, okay? And this is when the schedules become tricky and it's worthwhile to synthesize them because the humans cannot find them easily by hand. After all, browsers have tens, maybe up to 100 different attributes in them, okay? So what does this teach us about synthesis? Well, the layout engine is probably 100,000 lines of code. We clearly cannot synthesize all of it in one step. But what we can do is do abstract synthesis. Abstract in the sense that you synthesize some aspects of the code, here the schedule, and you leave the rest completely unchanged. So those statements we treat as black boxes. We only understand the dependencies between them, and we obey those during scheduling. Otherwise, they are completely unchanged. And this is the way of how to scale it, or one way to large software. So here is sort of a snippet of a scheduling language that your synthesizer may want to produce to determine how a fragment of CSS is scheduled, okay? This is a good point to move to how to build those synthesizers. That's something I didn't touch on, and I want to use the story of the synthesis of parallel layout engine as a motivator. So this is really what happened, okay? We started building the synthesizer without synthesis in mind. Originally, this project for parallelizing the browser was completely independent from our synthesis work. And of course, there exists a deterministic algorithm for building schedules for attribute grammars. After all, if you have all the dependencies in front of you, you just pick them one by one and you order those statements into a traversal so that they can all be computed by a sequence of up and down traversals, right? But we had to extend our grammar to have some software engineering properties such as interfaces, and that created so many new corner cases that we couldn't simply extend the algorithm. Truly, we had the master students working on the problem, and every week he came with more index cards with beautiful examples of more corner cases to the meeting, and we're trying to build an algorithm that would satisfy these. Eventually, we had something running, but it was fragile and it didn't generate the schedules that we wanted. So that was a clear failure and taught us that deterministic algorithm perhaps sometimes reach the point of you are not able to maintain them and extend them yourself. So what Leo Majerovic realized is that, well, it is easier to write a checker of schedules and search for the schedule and just check whether it is correct. And this is how he succeeded in synthesizing the schedule for CSS. The problem was that in order to write the search engine of the schedules, which he wrote in Prolog, he had to intertwine the search with the check to do early pruning in the space. He couldn't simply search and then check at the end. Those two had to be intertwined. The result was a Prolog mess that nobody could understand, so we had to eventually abandon this implementation. Okay? What happens in the end was we realized, wouldn't it be nice to just write a checker of schedules? You can think of it as the interpreter for the programs in the scheduling language, the fragment of which I showed you. And from that interpreter, automatically generate a search engine that will simply find a program from the language defined by the interpreter, okay, and gives you also a search engine. So this is what you get with ROSETTE, which is an approach that Emina Torlak, when she was in my group at Berkeley, pursued. So it is essentially a host language for building DSLs, but these are special DSLs. These are DSLs in the sense that they will include constructs for verification, synthesis, bug finding, and all of this by delegating to the solver. Okay? So how does it work? Well, it was all based on Emina's observation that all synthesis problems come with a DSL, so let's call them solver-aided DSLs and build a host language for building DSLs. And she took Racket, was very happy with it. It's a host language for DSL and extended Racket to be a host language for solver-aided DSLs. The story is that you build your DSL in the usual Racket way, no change here. And once you have the DSL becomes amenable to synthesis. You can just add constructs for verification, synthesis, create holes, specify what expressions will go where. And all this happens usually for free or nearly for free. What happens inside ROSETTE is a symbolic virtual machine, okay, which effectively does first Futamura projection, specializes away the interpreter, and just gives you formulas at the end, which you don't see, they go directly to the solver. So for the language of schedules, you would write an interpreter for this bottom-up, okay, bottom-up, top-down pass, and given that interpreter, you would get an automatic synthesizer for these programs. No interleaving of the search and the checking, because this is done automatically for you. So the challenge 3 is to follow on the philosophy of ROSETTE and say, well, there must be other problems out there that we are solving, which are essentially search or constraint solving. Okay? But what we do today, we write those constraints by hand, maybe in ILP, maybe in SMT. There is always a lot of work. And as we know anecdotally and ourselves, these constraints you often get wrong. Okay? So wouldn't it be nice if you could follow the philosophy of ROSETTE, which is write those constraints naturally, but just writing, say, an interpreter for the problem. So here is an example. In PLDI this year, there was a Cornell paper on finding diagnostics for LR parsing. You have those conflicts which nobody can understand. Wouldn't it be nice if you find two inputs and their parses that explain why these conflicts happen? Okay? Essentially, a search problem subject to constraints which encode what? Essentially the semantics of the LR parser. So what I would really like to do, get it for free, by writing no low-level constraints, no explicit search, by just 2 steps. Develop a regular parser, say in Racket. We know how to do that. And then I would like to annotate it with essentially questions for the search engine, which says, give me 2 inputs such that they bring me to this state and satisfy some other constraints. And yes, we can all do it today, but with a lot of spaghetti assertions and such. So there is a need for higher-level abstractions on how to write constraints in the natural way and yet pose these search problems. So that's challenge number 3, okay? And think of it as new solver-aided programming abstractions. Okay. Now I want to switch to something that if I ask my colleagues in synthesis what will happen during the next 10 years, 80% of the responses fall into this section. And this section is not very well organized because in this section is where most of the creativity will happen. There won't be a single theory that will cover everything. And this concerns what we can model with DSLs, and therefore where synthesis will be useful, and how we can actually put the human into the loop. Okay? So let's first talk about versatility of DSLs. It won't be surprising to you that you can model many things as programs, and that many processes, phenomena, and so on can be described with programs from DSLs. Some of them are not typically functional. Some of them are sort of regular expressions and such. Things about data cleaning, algebra, and other education. You've seen the talks by Sumit Gulwani, who beautifully explores this domain. But what's interesting to say that even hints for solving educational problems, the explanation of what went wrong in the student solution, can itself be written as a program, right? I think in ICFP is a community that understands from languages for animation that things that you typically don't think as programs can be written as programs. And of course, protocols and languages for modeling biology are programs too. So the list goes on and on. And so I just encourage you, anytime you're thinking of a problem that somebody brings to you, whether there exists a language for it, and it could be amenable to synthesis, and therefore generation from examples. The more interesting thing happens when you replace your verifier with a human or an experiment, a biological experiment, by going to the lab and testing a cell. Okay? So you get various flavors of programming by demonstration here. And I think this is where most of the creativity will happen, because usually we won't involve the human in the usual way. We are not asking the human to write just yet another input-output pair. There will be other ways how to query the human. And here I look forward to more results. So why more things will happen? Here it's good to talk about what specifications are like in our style of synthesis. Because specs are not the starting point for derivation for various axioms. There is a lot of freedom that we have, right? We can use as a spec anything that restricts the behavior. For example, input-output pairs, in fact, entire traces of execution, but also symbolic properties of the execution, post and pre and post conditions, right? And combination of those. More interestingly, the specs can be incomplete, okay? Because we can always consult the human oracle to resolve the ambiguity. For example, if I have a few input-output pairs, which narrows down the set of programs that I can synthesize, meaning these are programs that are correct on the given set of input-output pairs, I say, well, these programs disagree on some inputs on which the human didn't tell me what the behavior should be. But there is a set of inputs on which the programs do agree. So I can compute the precondition of those inputs on which the programs agree, and perhaps make the assumption that since they agree, I have a correct program for that subset, and only agree to run the programs on that subset. If you want to run it on those inputs where those programs disagree, programs correct with respect to current specs, that's when you involve the human. And then specs could, of course, be incorrect. Right? Mutually contradictory. And again, you can build a nice loop where you query the programmer to figure out how to resolve the conflicts in the spec. And another chapter is how to deal with uncertainty. Right? What if the human doesn't actually give you information? What if the information comes from the lab, from measurements? Well, then you have essentially two choices. You either build a probabilistic synthesizer, which synthesizes several most likely programs given the data, or it is a synthesizer of probabilistic programs, so you get a program that has stochastic semantics in it, and it gives you a distribution of the potential value. So depending on the setting, one or the other makes sense. How to build these efficiently, we don't know. This is a completely new chapter. Okay, so a little bit about systems biology. Systems biology is the science that takes measurements about cells, okay, proteins, genes, small molecules, and turns them into explanations of what the cell does. What is the genetic control? How cells react to stimuli? How they communicate to each other, and so on, right? Ideally, you would like to get a mechanistic program of the cell. Why mechanistic? Mechanistic in the sense that the program actually explains what the cell does, how proteins talk to each other, what determines whether a gene is transcribed or not, right? This would be useful because you could then find treatment for diseases and also predict their side effects. It would be fantastic. Currently, the state of the art in medicine and therefore systems biology is most of the time sort of pairwise relationship. You know that if you suppress the activity of some gene, okay, perhaps by introducing some small molecule, then that stops the cancer. So you know two things. If this, then that. but you don't know what else might happen. And that's why understanding the side effects would be useful. So if you compare this with that, it sort of reminds you of early program repair, right? If you write the value to a memory location, it stops the page fault, then maybe that's okay. But this is how a lot of sort of prediction on treatment is done today. So systems biology is at a critical milestone because now we are starting to get measurements that can help you turn what they call a hairball into a program. Okay, so what is a hairball? Each of the blue dots is, in this case, a protein, and there is an edge between them which says these two proteins interact. They may lock together, and if sort of one is suppressed, the other one goes up, or the other way around, essentially pairwise information. It's fair to call it a hairball. This is a program that may have different semantics depending on what data you actually have, but it may have a state machine which tells you what is the level of abundance of the protein over time. It may have a function which tells you how this protein reacts to this one, right? Here, this one typically increases with this one because it is activated. This one typically decreases because it is suppressed. By how exactly it is increased or decreased, of course, depends. So we want to get from something like this, with data that might look like that, there are different experiments, to a program like this on which you can say, well, if I introduce some effect here, it may actually have the desired effect, but it may also have a side effect. So I may want to start looking for something that will compensate for the side effect. Okay? What is the data here? Here is time. Okay? Each row is one particular protein, and the color shows you how much of it we have over time. So we would like to put these two informations together and synthesize the program. In fact, all programs that agree with the data and maybe compute an experiment. So here is how it looks like in a concrete setting. Here is a system introduced by Jasmine into our community. Each of these things is a stem cell. Okay. A stem cell has a receptor protein on it. Think of it as a TCP port. There are three more here that I'm not showing. Okay. And here is a so-called anchor cell. This anchor cell sends a chemical signal which tells these cells, in this cell division cycle, you guys are going to talk to each other, determine the leader, determine the secondary leader. That will be your fate, stem cell fate. After that, you start dividing and you will start forming different tissues. And because you form different tissues, you form an organ. So because this stem cell here is closest to the anchor cell, it gets a strong concentration of the signal. It will eventually reach fate number 1, a really descriptive number for a fate, but that's what it gets. It then signals to this cell, hey, I am the winner. You need to have fate number 2. You will be a different tissue. Okay? And then this one has a weak signal, so it will be 3, and it will be the third kind of tissue. So in this particular setting, what systems biology wants to do is synthesize this molecular program, which is effectively distributed leader election protocol. The program is built out of proteins. It's this, okay? We want to find out how exactly these proteins talk to each other that so robustly actually can compute this agreement in a distributed fashion, okay? Now, how do we do that? To infer this protocol, biologists essentially mutate the cell. They go to the cell and say, well, I will knock out this gene, the one that creates this protein in one experiment, and I let the organism grow and observe what happens. Okay? Then they do something else. Okay? And you get a table, which is a specification. Here it says, okay, in this one, this protein is turned off, and the 6 cells have these fates. Okay? This experiment is more interesting. We killed the anchor cell, the one that sends the chemical signal, and as a result, we get non-determinism, because nobody gets the signal, and there is sort of a race among the cells, and they have one of these two fates over there. They start signaling to each other. So we put into the synthesizer 2 things, a skeleton, a sketch of the model, which essentially just says how proteins we believe communicate, the mutation specification, so where the mutations are inputs and those fates are outputs, okay? And we get on the output 2 things. The description of those functions that protein obey, And more importantly, since we have two models, distinct but agreeing with the experiments, we get a computation of the experiment that you could now go to the lab and perform to distinguish which of these two experiments is actually valid. So this is sort of a scientific method where synthesis tells you, given the knowledge you believe you have, given the mutations you observed, you have one model, another model, and you can now go back to the lab and refine it, your hypothesis. Okay. So I want to conclude by synthesis of programming languages, which might be a strange title, but let's see how we got here, right? So synthesis is building on the shoulders of verification of model checking, of course. We would not be able to synthesize the program if we did not have the results, such as set solving, from model checking. So it makes sense that you continue and you model check a language and you synthesize a language. Why would you want to do that? Okay. And it will be less, surprising if you realize this language is essentially our abstractions. Instruction set architecture like x86, okay, or the crazy one that comes with the low power machine is a language of instructions. A type system is a language. The modeling language we use to define models of cells is also a language. So are memory models, storage models, APIs, and DSLs. And it seems feasible since we are already verifying and checking them, right? When we take a litmus test for a memory model and we compare it against the definition of the model, we really are checking whether the definition of the model, the language agrees with our assumptions, right? So we are a step closer to synthesis of the model. How do you synthesize it? Well, in theory, this is really simple because an interpreter is just a program, so we synthesize a program, and that defines the language. And that's essentially what we are doing in our early experiments. But what's interesting is how you formally pose the correctness condition. What is the spec? And what is that language for writing those interpreters, right? So let's visit this on memory models. So we know that they are notoriously hard. We know that they break optimizations, okay? We talked about it in the beginning. What the specification could be for it. So these litmus tests are small concurrent programs, some of them not so small, on which we say we believe we would like to get the following answer. And now if you have sort of a sketch of an interpreter for memory model, you can complete it so that you get a memory model that agrees with the litmus test, right? So you can think of it as a repair of an existing memory model. You could potentially, maybe, also come up with a memory model that allows certain optimizations. You would write one litmus test for the original program, then you would write another litmus test which is the same program optimized, and now you would ask for a memory model that executes the programs under the same semantics, right? Optimized than the original one as well. And it would also be nice if we could write those memory models in a language that reflects what's implementable in hardware, right? Ultimately, the memory model needs to have a cache coherence protocol and so on and so on. And it would be nice if we could actually get diagnostics when no such memory model exists. Okay? The similar thing exists in the biological language, where we want the language that allows you to synthesize a model that can reproduce your experiments, but not more. I don't think we want a model that is so accurate that creates many models that are syntactically distinct or semantically distinct, but there exists no experiment in the lab that would allow you to differentiate between them. So here we want to choose the modeling language based on experiments and the query at hand. And that's all I have. So the key ideas are that synthesis is search in a space defined by ADSL. The specification can be anything that gives the desired behavior or restricts behavior. You can construct a synthesizer by simply defining your DSL today. And then the refinement abstraction are tricks how to scale it to large problems. And programming and demonstration is one way of bringing programming languages to users and scientists. And I want to advertise a project that will be starting at UW soon, if all goes well, with 8 PIs who work really well together. It will include alvinization of the web browser and DSLs amenable to synthesis, adaptation, and so on. So if you are a student looking for grad school or a postdoc looking for a place to hang out, get in touch with us. And a big thank you to my research group who did, of course, a lot of the work. But needless to say, more than half of what I cited was done by other people. Okay. Thank you. Yes.
There's a mic. You just heard me, so I can speak again.
I can hear you.
Yomi. Programming languages are the interface between human beings and the machine and software, various layers. When you synthesize them, how do you bring this human interface element back? And human interface means two things, psychology and sociology.
Many ideas, right? Currently, a human designs the language such that it is a good interface, and that human has some set of built-in rules to follow, perhaps rules that are hard to state. I include your taste in it. So, no, okay. Maybe some design is done without taste. So the hope is that some of these things can be stated, if not formal rules, then at least examples, in the sense of, I don't know, I would like to have a language in which the following program can be written. To make it more concrete, think of a type system, and perhaps you know you would really like to type check a particular program for a particular property. And you believe that there exists a set of type rules that will allow you to type check it. Just there are these hairy corner cases that you cannot figure out. So I could bring the human element into it by posing those cases and say, give me a type system that works on those cases. Now remember what I mentioned at the beginning. I am not arguing for a completely automatic way of designing these languages. What I really want, and I think that's where the bright future is, nice interactive assistants. We already have proof assistants, right? There are many other kinds of assistants we can build. And so all I'm saying that for the designer of languages, we could potentially build those tools that will allow you to explore a design of the language much faster and therefore try other alternatives rather than committing to one early and sticking with it for a few years.
May I follow up? I intentionally mentioned the sociology and the socio-economic system around the language because of this last comment that I was expecting from you. I think a language evolves because programs are written to be read by human beings. And it's that process of communication between human beings that matters most about programs. And I would like to hear from you how you address that interpersonal, social aspect of the programming language.
So this is definitely a challenge for the next decade. So all I can do is speculate.
Yeah.
And so I'll speculate. And so imagine that you do have a tool that evolves your language, changes its definition, and rewrites all the programs that you have written in it, right? Okay. Otherwise, it's not as useful, but perhaps it's still useful. And now you need to guide that rewrite of the language in a particular direction, right? And that direction could be to say, well, here is a way of passing arguments into our language by reference, for example, that I want to eliminate, get rid of it while permitting all the programs that you still have written. So somehow I need to specify what the users don't like or what the users would like to have and make the synthesizer produce a language that has or does not have that feature. So it boils down to how do we state the wishes of the programmers, right? How do we pose the goodness or badness? And I don't know, but there are many people in the room who may have ideas. Perhaps what you are saying deep down is that we need to start paying attention to the soft aspects of language design and figuring out how to formalize them. And the formalization doesn't need to be the usual one. It just could be an example, maybe.
Yeah, provocative talk. Thanks very much. I was intrigued by you talking about not doing derivation but just doing search. When I think about stuff like the spiral gen approach of really using algebraic equivalences in order to make sure that you have something correct. And yet, on the other hand, if you're just doing search, it seems to me like potentially an intractable problem to be sure that you've ended up with something that is correct unless you can exhaustively search the space of all possible inputs. So I'm just wondering if you could just say a little bit more about that trade-off as to when you choose to use algebraic equivalences and use that to guide the potentially valid things in your search space versus just randomly trying things and hoping that you end up with something that's correct.
So the choice is very simple. When you have algebraic rules, use them. It just is the case that we don't have them for many domains. So there are a few domains for which we have algebraic rules, right? And they are sort of, let's call them domain.
So which ones don't you, I mean, give examples of ones where you can't perhaps even imagine algebraic rules.
Sparse matrices, for example, with all the optimizations that people do, such as blocking, prefetching, and such. I don't know of any rewrite system that allows you to take the specification of a linear algebra kernel and derive a sparse matrix.
And is your sense that they just don't exist or we don't know them, the algebraic equivalences?
I think they don't exist yet. So if we can create them, it would be fantastic. And if you want to use my talk as a call for creating these domain algebras, then yeah, let's do it. In fact, this would be probably the best community to start working on them. But so Spiral is great, right? What does Spiral do? It uses rewrite rules. Essentially, it puts 100 years of FFT, right, the research into a database and creates an FFT implementation by divide and conquer. Right? And it works great. We have such rules for dense linear algebra, regular expressions, parsing, relational algebra is another one. But these are really the only domain theories I know about that we can readily use. And if you think about it, each of these comes with a Turing Award. Not to discourage you. So I initially had wanted to include creation of these domain algebras as something that you could synthesize. But I don't know how you would get completeness and such. And so I sort of settled for mutations, which are things that are not semantics preserving, but help you with the search. So yes, if you use them, if you have them, use them. Now, about correctness, remember, we do search, but eventually correctness check happens through verification. It can be Horst-style in the sense that the invariants you need for the proof we can synthesize, if you need to. Turns out often you don't need to because the way synthesis is posed is often that you create these small chunks that are cyclic, right? And you synthesize those out of a bigger loopy program, and then you don't need invariants to prove them. You just do bounded model checking. Call it a plus if you want.
Early on, you mentioned generating specs for existing programs. What bodies, if any, are pursuing that? Like, and what work is being done around that? Because that seems like something that could be
right.
Very applicable very early on.
So that Alvinization example of taking a Java ORM code and lifting it up to a concise description in a relational DSL, I would call it coming up with a specification of an existing implementation. So Alvin Chang it would be one. But there are people in formal methods who try to do something similar, build essentially summaries of complicated implementations. Often they are abstract. So they may talk about timing and such. But abstract interpretation, in fact, is one area where people build specifications by analyzing code when they build summaries of procedures. So I'm happy to talk to you offline about other pointers. Thank you.